Cell 1. In this cell, we're delving into the key objectives that drive our optimization efforts within a retail context. Understanding these objectives is crucial because they guide our strategies and influence decision-making, ultimately impacting the performance of our campaigns. We're considering three primary objectives here. First, maximizing conversion, which focuses on increasing the probability that a shopper makes a purchase. This is essential because it directly correlates with overall sales and helps in identifying the most effective strategies to engage customers. Next, we look at maximizing revenue, which emphasizes enhancing the expected value of each shopping basket. This approach is not just about getting shoppers to buy, but also ensuring they're purchasing products that yield higher returns. The third objective is about increasing exposure to margin items. These include private label products or items on promotion, which often represent higher profit margins. By shifting shopper attention to these categories, we can significantly enhance profitability and optimize inventory. As we think about these objectives, it's important to acknowledge the balance needed between them. For instance, focusing too heavily on conversions may lead to overlooked opportunities for higher revenue items. Additionally, when exposing shoppers to margin items, we must ensure it's done in a way that feels natural and appealing rather than forced. In the next cell, we will likely explore specific strategies or metrics that help us quantify these objectives, allowing us to make data-driven decisions that align closely with our goals for improving retail performance. This will build on our foundation of understanding what we're aiming to optimize. Cell 2. In this cell, we're diving deep into simulating shopper behavior within a defined store layout. The approach uses random paths to represent how shoppers move and interact with various store categories, which is crucial for understanding consumer dynamics and enhancing marketing strategies. First, we start by defining a grid layout of the store with distinct sections like snacks, beverages, and a promotional area. This layout plays a vital role in guiding the simulated shopping paths. Each category has a specific margin associated with it, which later affects the revenue figures during the simulation. By assigning categories to specific areas within the grid, we create a realistic shopping environment that considers navigation patterns. Next, the simulation of shopper paths is framed as a biased random walk. It begins at the store entrance and progresses toward the checkout, while also enabling random wandering. As the shopper moves through the grid, they are attracted to categories based on their preferences, which we sample from a predefined distribution. This preference influences how they interact with specific store areas, like promotional zones or checkout sections. During their journey, shoppers experience various forces that influence their direction, including a gradual pull towards the checkout area. Additionally, there are mechanisms in place that simulate attraction to promotional sections, especially in the early to mid parts of their shopping path. We explore nearby cells and assess which category the shopper is currently preferentially inclined towards, allowing the simulation to reflect more natural exploration behavior. As we iterate through the simulation for multiple visits, we track key metrics like steps taken, unique areas visited, and how many times shoppers encounter promotional items. This data later contributes to a synthetic buying probability based on their experiences. Insights into exposure to the preferred category and the impact of congestion show how store layout and shopper behavior intertwine. Finally, we store the results of each simulated visit in a structured format, capturing details such as whether a purchase occurred and how much revenue was generated. This comprehensive dataset ultimately lays the groundwork for analyzing shopper interactions within the store, setting the stage for further insights in the next cell. Here, we'll likely explore deeper analysis or visualizations to glean actionable insights from these simulated shopper journeys. Cell 3. In this cell, we set the stage for building two predictive models, one for estimating purchase likelihood and the other for predicting potential revenue from buyers. This dual model approach is crucial because it allows us to understand both customer behavior and revenue potential, which can inform better business strategies. We start by selecting relevant features from our dataset, which includes various metrics like the number of steps, unique cells visited, and the day of the week. These features will serve as inputs to our models, enabling them to learn patterns in the data. The target variables are structured differently. We have a binary outcome indicating whether a purchase was made, and a continuous variable representing the revenue. Next, we split our dataset into training and testing sets, ensuring that we use 75% of the data to train our models and reserve the remaining 25% for validation. This random partitioning, governed by a seed value for reproducibility, is an important step to minimize overfitting and ensure that our models generalize well to unseen data. For the purchase model, a histogram-based gradient boosting classifier is employed, with specific parameters set for depth, learning rate, and iterations. The model learns to predict the likelihood of a purchase for each test instance. We also compute the area under the curve, AUC, to assess its performance. A high AUC score indicates better discrimination between buyers and non-buyers, which can directly influence marketing strategies. Moving on to the revenue model, we only consider those instances where a purchase was actually made. This logical filtering helps focus our predictions on relevant data. We then fit a gradient boosting regressor using the same features to estimate potential revenue. It's important to note that while our R-squared score appears low, this should not undermine the value of our findings. In this context, our primary goal is to reduce congestion and optimize flow, making revenue predictions a secondary concern, or as we might call it, a side quest. In conclusion, this dual modeling process equips us with insights not just about who might make a purchase, but also what revenue we could expect from them. As we transition to the next cell, we'll likely explore methods for optimizing these models and enhancing their practical performance further, perhaps by focusing on the operational aspects that support our primary objectives. Cell 4. In this cell, we're taking a fresh approach to optimization in a retail space by focusing on practical congestion metrics, rather than simply aiming for a high R-squared value. This shift is crucial because understanding how shoppers move and interact with the environment can lead to more effective solutions and improvements. We'll begin by evaluating key congestion metrics, which are directly linked to how often customers might find themselves obstructed or tripping over each other. Specifically, we'll look at the maximum number of shoppers in a designated area, which allows us to determine peak density. Rather than just relying on this maximum, we'll also consider the 95th percentile density, providing a more robust measure that accounts for typical peak conditions rather than extreme outliers. This inclusion allows for a deeper understanding of how space is utilized. Another important metric here is the time above a certain threshold, which captures how frequently the density exceeds a predefined number of shoppers, such as 3 people per area. This metric sheds light on the sustained pressure points within the layout. Additionally, we introduce a bottleneck score that considers not just the density, but also the flow rate, identifying areas where high density combined with limited movement creates serious congestion, much like a crowded hallway versus a dead end. On the flip side, we also evaluate flow and friction metrics, which can highlight where movement slows down. This includes measuring the average speed through different areas, where a slower pace can indicate congestion. We'll also assess the necessary detours that shoppers may take to navigate around congested areas, assessing how these detours affect overall flow. Furthermore, we will look at the queue time at checkouts or service counters and identify cross-traffic conflicts in zones where paths tend to intersect frequently, creating potential points of conflict for shoppers. As we proceed to the next cell, we'll be generating a plotly graph to visualize these metrics effectively. This will include labeling axes in a way that resonates with real-world dimensions, making it easier for us to analyze and interpret the spatial dynamics at play. The visual representation will help us understand where adjustments can be made for a smoother shopping experience. Cell 5. In this section, we're exploring a strategic approach to enhance store layout and improve customer flow. This is essential for creating a more pleasant shopping environment, ultimately boosting sales and customer satisfaction. The focus here is on how to optimize the placement of promotional displays and high-interest items, while also ensuring that walkways are clear and intuitive. The first concept involves splitting larger promotional end caps into smaller, strategically placed scenarios throughout the store. By distributing these promotions across different zones, we can capture shoppers' attention in multiple areas, rather than overwhelming them with a single display, which can lead to clutter. This method is particularly effective when we intentionally space out high-interest categories like snacks and beverages, preventing customers from being distracted or overwhelmed when these items are placed too closely together. Next, we tackle the idea of pull-through. By positioning destination items, like household staples and dairy, in less frequented areas of the store, we can effectively draw customers into these zones. This tactic not only increases visibility for items that might typically go unnoticed, but also encourages shoppers to explore parts of the store they might normally bypass. Another crucial component is addressing choke points in the store layout. By moving fixtures away from narrow corridors, we can eliminate blockages that slow down customer flow. The model treats these congested areas as obstacles, so shifting end caps to avoid protrusion into main traffic paths is vital for creating a smoother shopping experience. Additionally, for certain store formats, implementing one-way flow logic can greatly reduce head-on conflicts, especially in smaller spaces. Clear signage can guide shoppers along a designated path, making navigation easier and more efficient. As we move forward, the next cell will likely build upon these principles by diving deeper into specific measurements and analyses of how changes to layout impact customer behavior. This will help us better understand the effectiveness of our strategies and refine our approach even further. Cell 6. In this cell, we're setting up a visually engaging heat map to represent customer dwell times in a store, which can provide valuable insights into shopping behavior and product placement. By using this heat map, we can identify which aisles attract more attention and where customers may be spending most of their time. The heart of this code begins with the creation of the heat map using Plotly's capabilities. The variable heat contains the underlying data that informs us about the counts of customer dwell time across various sections of the store. We first create the figure, setting the color scheme to viridis, which is known for its clear gradient, allowing us to easily interpret the variations in dwell time represented by different colors. Next, we define the aisles and zones within the store. Each aisle is standardized as being 5 cells wide, meaning that the total width of the store, represented by the variable W, is divided evenly into aisles. This gives us a systematic way to label these aisles, helping us to easily reference them in our visual. We calculate the center points for each of these aisles, which serves as our tick marks on the x-axis for clearer labeling. Similarly, we section the store depth into 4 zones, which we designate as front, mid-back, and back. Just like with the aisles, we compute the center points for these zones, positioning them on the y-axis. This creates a 2-dimensional grid where the audience can infer customer behavior more intuitively. To enhance our heat map, we insert markers to highlight key locations within the store, such as the entrance, a promotional spot, and the checkout area. These markers not only act as reference points, but also enrich the narrative of the heat map, framing the data in context. With the layout of the plot configured, the resulting visualization provides a clear overview of where customers seem to linger, helping store managers make informed decisions. Looking ahead, we'll delve into further analysis based on this visual representation, perhaps correlating these dwell times with sales data or exploring additional variables that impact customer behavior. This transition will deepen our understanding of how physical store layout affects shopping patterns. Cell 7. In this cell, we're delving into the critical task of simulating occupancy over time, which is essential for understanding space utilization in our context. By generating a model of occupancy, we can make informed decisions about resource allocation or operational adjustments. The code encapsulates a function that takes in parameters like a heat map and event details to create an occupancy grid over a defined time frame. To begin with, we initialize our random number generator and define the shape of our heat map. The first key step is to calculate the probability distribution for placing occupancy events within the heat map cells, taking care to avoid any division by zero by adding a tiny constant. This results in a shape that reflects how likely it is for an event to occur in each cell based on existing heat values. We then randomly select the cells where these events will take place. After identifying the cells, we proceed to sample the start times for each event uniformly across the designated time frame, while durations are determined by a Poisson distribution, providing a realistic representation of how long each occupancy event lasts. The end times are calculated to ensure they do not exceed our defined time horizon. Next, the occupancy data is compiled into an efficient, cumulative sum array. This allows for a succinct representation of how occupancy changes over time without duplicating calculations. The function ultimately returns this occupancy matrix for further analysis. After simulating the occupancy, we calculate the average and peak occupancy within the space. These metrics help gauge overall utilization and point out any significant peak load periods. We then assess occupancy heats, particularly focusing on where we observe occupancy at the 95th percentile. Moving further, we create a time over threshold heat map. This metric indicates how often certain areas experience occupancy above a specified threshold, such as 3 shoppers in a single cell, giving insight into bottlenecks that may occur during peak usage. To highlight these bottleneck areas quantitatively, we compute a score that combines the 95th percentile occupancy and the duration of high occupancy. This leads us to create a sorted list of these bottleneck cells for later examination. Finally, we convert this data into a pandas data frame for clearer insights and easy manipulation. This lays the groundwork for effective decision-making regarding space management and optimizing customer flow. As we transition to the next cell, we will likely explore ways to visualize this bottleneck information or analyze it further to derive actionable strategies. Cell 8. In this cell, we're creating an animated heat map to visualize occupancy data over time using Plotly, which is an incredibly effective way to see how patterns change dynamically. The importance of this visualization lies in its ability to convey complex information through an interactive experience, making it much easier to grasp spatial and temporal trends. To start, we define the variable t to represent the number of time slices, derived from the shape of the occ array. This array holds the occupancy data we're interested in visualizing. As we loop through each time frame, we generate frames for our animation. Each frame is beautifully encapsulated in a heat map, displaying occupancy levels, with colors ranging on the Viridis scale. For clarity, we set the minimum value at 0 and the maximum at the 99th percentile of our occupancy data. This ensures that our heat map highlights meaningful variations while avoiding extreme outliers that could skew our perception. Next, we initialize the figure with the heat map for the first time slice. This serves as the anchor point for the animation. In addition, we configure the layout, giving our figure a descriptive title and defining axis titles to clarify what the viewer should be interpreting regarding the x and y dimensions. One key feature here is the embedding of buttons that let users play or pause the animation, providing interactivity for deeper engagement. We've also integrated a slider that allows users to manually navigate through specific time frames. Each step on this slider corresponds to a time slice, making the visualization adaptable to individual preferences. A potential pitfall to be mindful of is ensuring that the data in occ is well prepared. Any unexpected values could compromise the clarity of the visualization or lead to misleading interpretations. As we move forward, the next cell will likely build upon this captivating heat map by perhaps introducing further analysis, additional features, or even integrating more complex data interactions. This enhances not just the user experience, but also the depth of insights we can derive from our visualization. Overall, this animated heat map offers a powerful glimpse into dynamic patterns, laying the foundation for richer analyses down the line. Cell 9. In this cell, we're creating two static heat maps using Plotly to visualize occupancy metrics and time exceeding a specified threshold. These visualizations are crucial for understanding performance, as they help identify patterns or anomalies in data that may need further investigation. The first part of the code constructs a heat map to represent the 95th percentile occupancy values, referred to as P95. The heat map uses a color scale called viridis, which provides a clear visual representation of the data intensity across different dimensions. The accompanying color bar ensures that viewers can easily interpret the scale, while the layout adjustments give it a polished appearance. By establishing a fixed aspect ratio with the y-axis anchored to the x-axis, we maintain a consistent perspective, beneficial for comparing values directly. Next, we move on to the second figure, focusing on the time that exceeds a defined threshold. Similar to the first heat map, it employs the same color scale and layout principles to present this critical metric effectively. It's important to note how using consistent visual designs across the two figures enables better comparative analysis. We even specify the threshold in the title of the heat map, highlighting how it relates to the data. As we proceed through this analysis, a key consideration for learners is understanding how these visualizations correlate with the underlying data. The heat maps can reveal trends that may necessitate further study, offering insight into when and where occupancy issues arise. Additionally, learners should be aware that color choices and scaling can impact interpretability. Using thoughtful design principles can enhance engagement and comprehension for various audiences. Looking ahead, we will likely build on these visualizations, perhaps by incorporating interactivity or diving deeper into the implications of our findings. This will enhance our ability to draw actionable insights from the data, further informing our analysis. Cell 10. In this cell, we delve into analyzing occupancy data to evaluate congestion and identify hotspots within a space, which is crucial for understanding how well a space is utilized and where improvements can be made. We begin by determining the peak occupancy at a particular cell during the worst time, and then assess the overall peak occupancy across the entire area, which allows us to identify not just individual problem spots, but also broader patterns of crowding. The first key step involves calculating the maximum occupancy recorded at any single location. This helps pinpoint the worst-case scenario in terms of crowding. Subsequently, we look at the total number of people in the store during peak hours, providing insight into general attendance trends. Another important aspect of this analysis is to measure the congestion burden. By comparing the occupancy data to a predefined threshold, we can quantify how many locations exceed acceptable crowd levels. This step ensures we can gauge whether the space is under too much strain. Next, we examine the average occupancy across all cells, transforming that data into a probability distribution. This leads us to the computation of entropy, which informs us about the spatial distribution of people. A higher entropy value indicates that people are spread out more evenly, while a lower value suggests clustering. This distribution is further refined by assessing the top 10% of the most occupied areas. Examining this share lets us understand concentration better. Lower values indicate a balance in how space is utilized. Finally, we assess how many bad cells exist, specifically those where occupancy has consistently been high over time, helping identify persistent bottlenecks. Throughout this analysis, it's essential to be cautious about assumptions related to occupancy and threshold values, as they can significantly influence interpretations. As we glance ahead, the next cell is likely to build on these insights, perhaps by offering strategies for improving space utilization or analyzing how these patterns change over time. This kind of forward-thinking approach is imperative for proactively managing occupancy in bustling environments. Cell 11. In this cell, we focus on redistributing dwell time across a heat map to optimize layout and improve user engagement. The essence of this process lies in strategically moving dwell distributions from the hottest to the coldest areas, which can lead to a more balanced and effective layout. To achieve this, we introduce a function that reallocates a specified fraction of dwell time, which is essential for examining how shifts can change user behavior in a spatial context. The function begins by examining the total dwell time. If it's 0 or less, it simply returns the original heat map, as no adjustments would be meaningful. It then organizes the heat values and identifies which areas are the hottest and coldest based on their dwell times. The redistribution occurs in two main steps. First, the amount to move is determined, and then it proportionally distributes that amount from the hottest cells to the coldest cells. This is crucial, as understanding how shifts in attention can influence user interactions allows for more informed design choices. Throughout this process, the algorithm uses randomization and scaling to ensure the transition is both smooth and reflective of real-world interactions. It's worth noting that introducing randomness can lead to variability in outcomes, so keeping an eye on this can help avoid potential pitfalls. After modifying the heat map, a simulation of occupancy based on the new heat values gives insight into how user presence shifts in response to the changes. We then compute several key performance indicators like the peak and average occupancy, entropy, and the share of top categories to assess the impacts of our redistribution. By comparing the original and modified metrics, we can gauge the effectiveness of our layout adjustments. Looking ahead, the next cell will likely build on these insights by exploring further adjustments or validations of the layout. As we refine our approach, understanding these metrics will be critical for iterative improvements in user engagement strategies. Cell 12. In this cell, we're diving into some important metrics that capture how changes in occupancy impact crowd behavior within a system. These metrics provide insights on both the worst-case scenarios and the overall distribution of crowding levels, which are crucial for understanding how effective our adjustments have been. First, let's look at the concept of peak cell, which reflects the maximum occupancy observed in a single instance. The key takeaway here is that while we've seen an improvement in terms of the worst-case scenario, moving from a peak of 186 down to 175, this data alone doesn't tell the whole story of how crowding has shifted overall. Next is the burden, which gives us a sense of how frequently cells exceed a set threshold of occupancy. Despite the peak improvement, our burden metric shifted from 0.197 to 0.209, indicating that overcrowding has become slightly more common. This situation highlights the classic trade-off we've encountered. While we've mitigated the worst overcrowding moment, we've inadvertently allowed more medium levels of congestion to spread throughout the system. Now, onto the entropy value, which measures how evenly traffic is distributed among the cells. Here, we observed a positive change, where the score improved from 4.49 to 4.58. This increase indicates that shoppers are more evenly dispersed, which is a favorable outcome since balanced distribution can improve overall consumer experience. Following that is the top 10 share metric, which focuses on the concentration of traffic in the busiest cells. Again, we see positive results with a reduction from 0.807 to 0.770. This drop signifies that occupancy is less clustered in a few hotspots, aligning well with our improved entropy figure. Finally, we assess the bad cells count, which identifies the number of cells that remain overcrowded for significant periods. Unfortunately, this metric has risen from 148 to 155, suggesting a trend where more areas are displaying persistent crowding issues. This echoes our burden results, reaffirming that while we've tackled severe cases, moderate congestion has become more widespread. What we observe here is not a simple win-loss situation, but rather a nuanced trade-off. Each metric reveals a different piece of the puzzle, compelling us to weigh the benefits of reducing extreme congestion against the rise in more commonplace crowding. As we transition to the next cell, we'll likely explore further adjustments or strategies that can help us balance these competing concerns more effectively. Cell 13. In this cell, we're validating whether the new heat data, stored in the variable heat new, truly differs from the previous dataset. This step is crucial because it allows us to ensure that our calculations or adjustments have effectively produced a revised dataset. By comparing the two arrays, we can assess the integrity of our updates. First, the code checks if heat new and heat are referencing the same object in memory, which is a fundamental yet often overlooked aspect in programming. This is done using the is operator, and while being the same object would mean no changes occurred, this check alone isn't enough to confirm differences in values. Next, the script uses NumPy's array_equal function to determine if the values within heat new and heat are exactly the same. This step is significant because two arrays could be distinct objects in memory but hold identical data. The heart of the analysis follows with a calculation of the difference between the two arrays, yielding crucial insights into our changes. We then print the total sum of the old and new datasets, which provides context on how our modifications have affected the overall heat data. Furthermore, we dive into the specifics of these changes by calculating the maximum absolute change for any single cell and the total sum of all absolute changes. These metrics offer a clearer picture of the scale of the differences, and with this, we can gauge whether our adjustments are substantial or negligible. Lastly, the code counts how many cells have undergone changes, allowing us to quantify the impact of our operations. It's essential to remain vigilant about any assumptions during this process, especially regarding data integrity and the initial state of the heat variable. Looking ahead to the next cell, we'll likely leverage these comparisons to guide further analyses or visualizations, building on the validation we just performed to draw deeper conclusions from the data we've prepared. Cell 14. In this section of the notebook, we're focusing on visualizing two heat maps side by side, which is crucial for comparing the original heat distribution with the modified version after applying the redistribute heat function. By using the same color scale for both plots, we enhance our ability to identify differences more easily, offering a clearer insight into the data. The code achieves this by first calculating the maximum value for the color scale. This is done using the 99.5 percentile of the combined values from both heat maps, ensuring that outliers do not skew our visual comparison. Setting the minimum value to 0 establishes a clear baseline, allowing the viewer to interpret the intensities effectively. A subplot is created to accommodate both heat maps, ensuring they share the same layout. The original heat map is plotted first, followed by the new, modified heat map. Each heat map uses the Viridis color scale, which is well regarded for its perceptual uniformity, thereby making it easier to discern gradients in data. Furthermore, an important feature here is the absence of a scale bar in the original heat map, which prevents cluttering. Instead, we've included a color bar in the modified heat map to enable precise interpretation of the dwell metric. To maintain visual alignment, adjustments ensure that the y-axes are scaled consistently across both subplots. As we move to the next cell, we will likely delve deeper into the data insights that emerge from these visual comparisons. This analysis will help us understand how the redistribution of heat affects overall performance and inform any necessary adjustments moving forward. Cell 15. In this cell, we're visualizing the differences between two heat distributions by creating a difference map. This kind of visualization is crucial for understanding how the newly computed heat values, referred to as heat new, differ from the original heat measurements. By plotting this difference, we can easily identify areas of significant change, which may indicate important shifts or trends in the data. To achieve this, we first calculate the difference by subtracting the original heat distribution from the new one. This operation results in a new matrix, where each element represents how much the value has changed, whether it is increased or decreased. The logic applied here emphasizes visual representation, allowing us to quickly detect which areas have higher or lower measurements. The goHeatMap function is then employed to create the visual output. By setting the color scale to RDBU, we provide a clear indication of increases and decreases, with shades of red indicating areas of increase and shades of blue showing reductions. The layout is also carefully adjusted to enhance readability, setting a meaningful title that explains the nature of the data being shown. The color bar accompanies the heat map, offering context on what those color changes mean in terms of the delta dwell. Notably, the scaling of the axes ensures that the representation is proportional, making it easier to analyze patterns across both dimensions. As you explore the output, it's important to keep in mind any assumptions regarding the data. For instance, ensure the dimensions of the matrices align correctly. Adjusting the figure's width and height offers a better view of the details, preventing any overcrowding or loss of information. In the upcoming cell, we will likely build on this difference map visualization, perhaps by analyzing these changes further, or applying statistical tests to quantify their significance. This next step could provide deeper insights into what drives these variations and their implications for our broader analysis. Cell 16. In this code cell, we delve into constructing a layout optimization score by assessing various key performance indicators, specifically entropy, top 10 share, peak cell, burden, and bad cells. This step is crucial as it helps to quantitatively evaluate the efficiency of occupancy across different layouts, allowing us to make informed decisions based on solid metrics rather than intuition alone. The first function, Gini, calculates the Gini coefficient, which gives insight into the distribution of occupancy. Essentially, it helps us gauge inequality, with lower values indicating a more equitable distribution. Following that, the metrics plus function aggregates multiple occupancy metrics, including the 95th percentile of occupancy, the mean occupancy across time, and the proportion of cells exceeding a specified threshold. Each of these metrics contributes to a comprehensive understanding of how the layout performs under varying conditions, such as peak usage and overall burden. Next, we move to the objective function, which is pivotal for optimization. Here, we assign specific weights to each metric. The aim is to minimize congestion and concentration, which means a lower objective result is preferable. Interestingly, we penalize higher values of peak cell and bad cells, while rewarding greater entropy, as a higher entropy implies a more balanced use of space. The run experiment function serves as a critical experimental framework, allowing us to test our layout optimizations across different random seeds. It simulates occupancy in both the original and proposed layouts, calculates the metrics for both setups, and ultimately returns the results in a structured format. This framework is vital for demonstrating that observed improvements are not simply random occurrences, but rather the result of systematic analysis. Finally, we summarize the differences between the two layouts by calculating the mean and standard deviation of the changes in objective scores, providing a clearer picture of efficacy. As we proceed to the next cell, we will likely shift our focus toward interpreting these results further, perhaps visualizing the data for easier comprehension, or exploring the implications of our findings in greater depth. Cell 17. In this cell, we're creating a KPI scorecard that summarizes the before and after performance of several key metrics. This is vital for assessing the impact of any changes or interventions we've implemented, allowing us to make data-driven decisions going forward. The function defined here, summarize, calculates several critical statistics for the metrics we want to evaluate. It takes two columns as input, one representing the baseline metrics and the other capturing the new metrics after changes. The function computes the mean values for both periods, the absolute change between them, and the percentage change, which gives insight into growth or decline. An important aspect is how it determines the improvement rate, which indicates whether the metric has improved, based on whether lower is better for a specific measurement. For instance, metrics like bad cells or burden are ideally minimized, while something like entropy thrives on higher values. Next, we loop through our defined set of KPIs, pulling data from the data frame for both the baseline and updated metrics. There's a conditional logic here that adjusts the calculations for metrics like entropy, which require flipping the improvement rate logic since higher values are favorable. This careful handling ensures we're accurately interpreting our results. Finally, we compile these results into a new data frame, aptly formatted to provide a concise yet informative comparison of the metrics before and after the changes. After building the scorecard, we display it, giving a clear visual representation of the outcomes. As we move forward, the next cell will likely explore how to interpret these results in a practical context, helping us draw insights and guide our next steps based on this data. Cell 18. In this cell, we're diving into key performance metrics that help us understand the impact of recent changes on our system's efficiency. These metrics not only quantify various aspects of performance, but also help us identify areas for improvement. Starting with the peak cell, we see a notable improvement with a reduction of almost 6%. This indicates that the worst performing bottleneck has been alleviated across all iterations, which is an encouraging sign. Meanwhile, the burden metric has increased by over 6%, suggesting that overall congestion has worsened, particularly with no improvements noted in this area. This highlights a critical issue. While we've reduced specific bottlenecks, it may have inadvertently led to a greater total time spent above the congestion threshold. Next, we observe the top 10 share, reporting a 5% improvement and indicating that traffic is less concentrated in the busiest cells. This is vital because a more even distribution can often lead to improved overall performance and efficiency. On the inequality front, the Gini coefficient shows a slight decrease, revealing that space usage has become more equitable, which is a positive trend. Interestingly, the number of bad cells has risen, indicating that more areas are now experiencing moderate congestion without any improvement. This serves as a reminder that while we may have targeted specific problems, we shouldn't lose sight of new issues that can arise. The entropy metric furthers this narrative, showing an increase that signifies traffic distribution has become more uniform across the system. In essence, these metrics weave a complex story of progress and challenges. The key takeaway is that improvements in one area can sometimes lead to unintended consequences elsewhere. As we move forward to the next cell, it will be vital to explore strategies to address these emerging challenges while maintaining our gains in overall efficiency. Cell 19. In this cell, we delve into the critical intersection of physical retail space and the insights we can gain from machine learning and heat maps. This approach is essential because it helps retailers uncover hidden costs and revenue opportunities tied to customer movement, laying the groundwork for more effective store layouts and strategies. To understand how this works, let's break down the core business challenges faced by traditional retailers. They operate under tight constraints, including fixed space due to high rents, human movement that can hinder customer flow, and importantly, limited shopper attention, where customers can easily overlook products. Poor store layouts can lead to congestion, resulting in frustrated customers who leave without making a purchase. Additionally, if customers can't easily access or see products, retailers miss out on potential sales, which also leads to inefficient labor, where staff may struggle to assist customers due to overcrowding. However, traditional metrics like sales per SKU or revenue per square foot often fail to capture these dynamics fully. They overlook crucial aspects, such as where shoppers intended to go but couldn't, or where they may have become stuck. Heat maps provide a remedy by visually illustrating these patterns, showing, for instance, that high dwell time does not necessarily equate to high sales. In fact, heat maps can highlight bottlenecks in areas that seem successful, revealing dead zones with virtually no foot traffic, as well as areas where customer collisions frequently occur. But heat maps are only descriptive. That's where machine learning comes into play. While heat maps tell us where customers are standing, machine learning can offer predictive insights that guide actionable changes. For instance, it can forecast the impact of relocating certain products, or assess how different layouts might perform on weekends compared to weekdays. This allows retailers to optimize their floor plans with confidence, ensuring that changes will have the desired effect on customer experience and sales. By combining heat map data with machine learning, retailers can tackle concrete business objectives, whether it's increasing revenue without expanding footprint, enhancing customer experience by reducing congestion, improving labor efficiency, or ensuring safety compliance. This sophisticated analysis provides a roadmap for smarter assortment and merchandising. Looking ahead, the next cell will likely build on this foundation, exploring tangible case studies that illustrate these principles in action and how they can drive decision-making in real-world retail settings. Cell 20. This cell serves as a conclusion to our Jupyter Notebook, encapsulating everything we've discussed and allowing us to reflect on the insights gained throughout the process. It's a crucial moment to solidify our understanding of the material we've worked through, tying together the theories and practical applications. In this cell, rather than executing code, we're simply marking the end of our exploration. It's a signal that all previous computations, analyses, and visualizations have led us to this moment. As such, it encourages us to think critically about what we've learned. Have we reached any conclusions? Do we recognize the broader implications within this subject area? This is also a great time to consider how the steps we've undertaken can be applied in different contexts. For example, if we were working on data analysis or machine learning, we should think about how the results we've gathered could influence real-world decisions. Additionally, we should reflect on any assumptions we made, as these often shape our understanding of the outcomes. The journey doesn't end here. We'll soon transition into a new phase of our learning. The next steps could involve deeper analyses, further exploration of alternate methods, or even preparing to share our findings. Each cell has built upon the last, and this conclusion paves the way for new ideas and directions in our continued study. So let's carry this knowledge forward and prepare for the exciting challenges that lie ahead.